Hi everyone, and welcome to my interview with Mark LaLiberte. I actually recorded this session a few days ago, and I had my fellow draftsman, fellow energy rater and co-host Darren Bowman along to help me. It was a Zoom webinar format. Now, full disclosure here, I messed up the start of the recording, which is why I'm recording this today. Luckily, all I really missed out on is the introduction, and a bit of the background as to why I was doing this. So I'll kick off with the background. The background is I've been doing building design for a very long time, and when energy rating came into what we do, I jumped into that pretty early on because I had a reasonable understanding of it. But from day one, I was a little bit frustrated about the guidance we were receiving and as far as what we were doing, and saw some potential problems with overheating of houses and moisture problems. So before Passive House became a thing in Australia, I actually contacted them when they were in Germany to find out what they do, just to compare it to what we do. I also looked at the USA to see what they do in comparison to what we do. The USA appealed to me mainly because their construction methods are very similar to ours, and their climatic conditions in certain areas are very similar to ours. So it was more of a direct comparison. This is where I was introduced to the term building science, and that's what they focus on in the USA. Like Passive House, they have a whole house approach to buildings for building performance under the building science methods. So I did a lot of study online, a lot of YouTube. So I've actually known Mark LaLiberte for a lot longer than he's known me. I ended up going to the USA in 2019 to the International Builders Show, where I heard Mark speak. After Mark's presentation, he was kind enough to speak to me one-on-one. We had a really good chat and talked about all of my frustrations and all of his knowledge, which I really appreciated. I ended up going back to Denver later that year to have some building science training at Mark's facility in Denver at CI Live. And since then, I've built a really good relationship with the CI team, and in particular Mark, and I speak to Mark a bit on the phone every so often, and we talk about ideas to each other, which is really good. So I'm just going to jump into the introduction to give you an idea of who Mark is, because a lot of you might not have heard of him. In the USA, he's a pretty big deal, and he's a very sought after building scientist. So here's the introduction. Mark is the co-founder and president of Construction Instruction in Denver, Colorado. Mark also leads the CI team to provide next level of training at CI Live. This facility incorporates a classroom, mock-up walls, structural assemblies, a custom-built house, and lab experimentation to define the best practices of entire building systems, from framing to advanced HVAC. Mark has dedicated over 30 years to the building industry. He is known for his Building Better Homes video series and his lecture series. Mark is constantly traveling all over the USA, teaching people all about building science. Mark also developed the industry-leading CI app, which is free to download on iOS or Android. That's really worth looking into. Mark achieved a Lifetime Achievement Award from the Energy and Environmental Building Alliance, where he developed the highly acclaimed Houses That Work lecture series. That lecture series has been running for over 20 years now, and it's all about building houses that actually work. Look, I could go on and on about Mark's credentials and his awards, but I just wanted to impress on you what a leading light he is in the USA, North America in general. He's very sought after, and we were very lucky to have him along, and I'm very grateful that he actually offered to speak to me and to answer our questions. So with that, apologies for messing up the original video, but now we'll just cut back to the interview. Thanks, everyone.
Ever win that. And so as long as we appreciate the fact that there are strong parameters along what it is that we're talking about, you'll realize that most of the building science physics is pretty clear and done. All we have to do is now begin the process of executing on what we know. So that's kind of my little brief over dissertation. So Greg, please start wherever you'd like to.
Okay, well, I was going to start with what is building science, but you've already told us that. So that's a pretty good one. So basically, Mark, here our houses are predominantly concrete slab on ground. They're stick-built timber, the same, or wood. We say timber. There are a few terminology things that are different. We don't sheathe our houses. And I think in Arizona, you don't sheathe yours either. Is that correct, on the walls?
Correct.
But
That's
you
correct.
do on the roof?
Yes.
Yep, okay. We don't on the roof either. Okay. So
I think the main difference with the reason we wouldn't do the roof is perhaps the different material we use for roofing. Mainly either metal sheeting, or which can span between battens, or clay or concrete tiles, which are laid on battens.
Yeah. So sorry, Mark.
Go ahead. No, I think it's, if you look at European buildings, don't use sheathing either. Sheathing is really an interesting exercise. I don't know if you are all paying attention to the lumber issues in the North America, but it's a disaster. And the price of forget a sheet of plywood, for example, has gone from a year ago. It was running about probably be $18 to $20 per sheet. It currently runs for about $80 a sheet. So it's on the rise. They don't see any too much relief in sight, maybe till the fall. We're in a housing tear, which is the largest housing construction boom since 2006. And we can't find labor or materials. So it's quite a challenge. When you look, Greg, at sheathing, I guess part of it has always been that the sheathing invention is really in the 50s with the invention basically of plywood. And it was just to provide kind of a faster way of creating shear across the building assembly. And the assumption was that you could also do that on the roof and kind of create this kind of monolithic assembly. Using battens across that in other parts of the world is done. In Arizona, they sheathe the buildings and the roofs, and then they put wood battens down across the roof, and then set the tiles against that. So they have a layer of building paper, a wood batten, and then a tile sits. Just so you know, most of those roofs rot out. The water runs down the sheathing, gets stuck at the wood batten. There's no ventilation between the batten and the thing other than a little gap, and the wood battens rot out in about 15 years. So there is some reason why it doesn't always work.
Yep. Okay. So what we might do, Mark, if we start with the basics of building science, the control layers maybe, water, air, vapor, and thermal. And we'll also get into ventilation as well. As I know, when I was talking to you on the phone last week, you're all over the ventilation thing. That's your big thing at the moment. And as there are quite a few people here who are probably wanting to hear a fair bit about that. But for a start, with our water layer, we use house wrap, which you call WRB. Could you tell us what WRB stands for?
Well, the term is weather resistive barrier. We're always really careful to be careful about what we call that. It's really not even a weather resistive barrier. There's debate about that. It's called a water control layer, basically. And so it doesn't really battle the weather, it battles water. And it can battle air as well, because if it's continuously or built together as one system, it can also reduce air leakage into the building. But primarily its function is to manage water.
Yep. And with the WRB, or our house wrap, you put quite an emphasis on flashing around openings and taping. Can you just talk us through that?
Yeah, it seems pretty goofy the way we do things. I mean, you wouldn't tuck your rain pants into your boots or your rain jacket into your pants, right? So making sure that everything is lapped and shingled is critical. But when we look at the fact that the cladding systems that go on buildings oftentimes allow wind-driven rain to get past almost everything. In the research center we have in Denver, we put buildings under pressure that represents about a 60-mile-an-hour wind, and we introduce rain to it. And almost all conventional building approaches that are being used leak profusely. And they leak into the wall assemblies, and then it's able to cause either some decay or hopefully over a short period of time dry. But weather resistant barriers must be an airtight or a watertight assembly on the building. so that any penetration is then flashed to the outside. Windows, for example, windows leak. We need to all agree as an industry and as a group here today, we're all going to say windows leak. And if you say it out loud, then it becomes a reality. And realize that as you put a window into an opening, it's the connection to the building. It's the parts move and expand and contract. If water ever gets by the window, all I want to do is let it to leak out. I don't care if it leaks. I just don't want it to leak in. So all of the penetrations in the building, which are numerous, all the attachments need to just make sure their eyes flashed back to the outside. Everything's good. So nothing but net, as long as you've flashed the building in all configurations to the outside, and sealants help us maintain a long-term durability.
Yep. Okay. So that's our water barrier. The next one in the list, and we've got what, water, air, vapor, and thermal, all in that order, and in that order of importance as well.
Perhaps just before we move on, Greg, Rich just made a point. Is that WRB vapor permeable?
Most often it is, yeah, it should be. There are other types in the marketplace. It's a good question if they are, Richard, but the challenge ends up being that if the assumption is that should water get past the WRB and be able to dry back out, or should the water originate, the moisture originate from inside the building, you'd want it to then move through the assembly. And then as long as that layer was free to breathe back to the exterior, I'm always careful about the term breathe, but making sure that the water molecules can then freely migrate to the outside. If it was a vapor control layer, in other words, a vapor impermeable layer, moisture from inside the building trying to travel to the outside would then of course be stuck and not allow that to happen. Yeah. So if we build a watertight building, which is critical, we have some different characteristics. Let's say that and pretend that the layer was watertight. Let's say it was vapor tight. If you live in a climate where there's humidity, Greg, you have any places down there that are humid?
Oh yeah, certainly do.
Of course. So if they're air conditioning on the inside, for example, and there's a lot of humidity on the outside, I might want more of a vapor impermeable layer to make sure that that water vapor didn't move through the building and then get to the inside. As it got to the inside where I'm air conditioning, I run the risk of reaching dew point. Yep. So in some of the southern markets, we have a lower rate of permeability. In the more northern markets, we oftentimes see a little higher rate of permeability. Now, the permeability issue is also in debate. How much does it need to be? How high should the level be? Those are always little things that get bounced around, but in general, and Richard's question is, we would like to see some vapor permeability of that weather barrier. Most people here would agree that a 20 perm or greater permeability would be preferred.
Yep. So, and Richard, also when we're talking about 20 perms, we've got difference between how it's measured in the USA and here. We have the SI units, so we'd have to look into that. But generally down where we are, a vapor permeable membrane is what.
Yeah, it might be worth just mentioning climate too. Richard also asked the question whether our climate would be similar to California. I think we're looking at the Golden Gate Bridge behind you, Mark, but
yeah,
you're in Colorado.
I'm in Arizona, actually, but yes.
Oh, sorry, Arizona, yes. But that's a different climate altogether, isn't it?
Yeah, well, just so you know, I grew up in Minnesota. Temperatures are minus 20 degrees Fahrenheit and 100 degrees in the summer. I moved to Denver, where they are down to 0 degrees in the winter and up to 100. And I live in Phoenix, where the temperatures can range between 100 degrees Fahrenheit and maybe get down as low as 30. Minnesota being about 40 inches of rain a year, Denver about 15, and Arizona about 4. So I've lived in all climate zones, but worked in almost every climate zone.
Yeah. And construction instruction is based in Denver, is that right? Yeah.
That's correct.
Yeah. Okay. So, all right, Greg, do you know the equivalent climate in the US?
Yeah, it's sort of, Richard's close to it. When I've looked it up, it's sort of around Oakland, San Francisco, roughly the same temperature range. Our summers can get a bit hotter. The difference is, and rainfall is very similar, but this is the thing that we have to be a bit careful of, even when we compare ourselves with New Zealand or Tasmania. Australia is about the same size as the USA landmass, but mostly desert. So we have a greater drying capacity.
Yes, you do.
So even though we can say it's pretty similar to around San Francisco, with a similar rainfall, our drying capacity is greater. So it's actually better for us.
It is.
San Francisco, they'd have a few more damp problems than we do because they're surrounded by water. That's the other thing too. If you're surrounded by water, then the humidity is going to be higher.
They also have high vapor clouds. I was just in Monterey last week, and in Monterey they have fog layers that come in for a good share of the day.
Yep.
The drying capacities are substantially reduced in that configurations.
Yep. So we do have the issue, but it's just to what degree. So in comparison, we're not quite as bad. So and it's very, very hard to pick another place in the world and say we're the same as that. But yes, once you understand
there's no need to do so. And I would encourage people to realize that climate isn't the great differentiator. We believe that we can build airtight, thermally insulated buildings in Seattle, and they should be built like similar in Arizona, as in Minnesota, as in Florida, as in Australia, and in Germany. So it isn't critical that you pick your climate and say, yeah, but we're different. Physics are the same. Remember that. Gravity is the same. Water vapor moves from a concentration of more to less. Heat flows from a concentration of heat flowing from warm to cold. Those are the fundamental physics. So what we have to do is stop allowing ourselves these great differentiations between climate zones and realize that any building built to be watertight, thermally insulated, airtight, and then managing the issues of vapor can function almost anywhere.
That's correct. Well done, Mark. Because one of the issues we have here is we're very focused on energy efficiency, and passive solar is a big thing as well. So we've gone down that path and we haven't really embraced the building science or the whole system approach to buildings. Right. Once we do that, then what you said is spot on correct. And
well, here's what happens. I have a long background in passive solar. The challenge with passive solar is it looks really cool. It is true that the energy coming into the building is nearly free. It provides us very little control unless you're extremely good at understanding mass. So if I have a building and I say, I don't mind it going from 50 degrees to 90 degrees, you're like, go ahead, go passive. If people are saying, I want to be somewhere between 71F and 75F, then passive doesn't work as easily. So you've got to make sure you appreciate the fact that variations in climate as well as times of year give you a differentiation in the angle of the sun. So because you guys have the sun out of the north, you realize that regardless of north or south in terms of hemispheres, we appreciate the fact that if the sun's coming in through a window, we can be very happy until it's gotten to be too much. And now my challenge is, how do I get rid of that excess heat? I'm a big fan of the fact that I want a very well-insulated building, and that's because I can now control the enclosure. Whatever passive solar does come in, I can retain that and then use that as it's intended. The book I studied when I was in college was the Passive Solar book by Ed Mazria, published in 1981. So the strategies there are sound, but still remember, airtight, watertight, and thermally efficient. Then I need smaller amounts of energy, whether it's free from the sun or from the electric grid. But the idea is to build that enclosure really well done. And then, as you said, the ventilation proponent is critical.
Yep. So we're talking about optimizing solar gain, not maximizing solar gain.
That's correct. If you maximize the solar gain, you'll run the risk of having an overheated building. You guys have beautiful sun there, and you will overheat buildings. And so you have to be careful. Now, you can pick glass that has a very high or very low solar heat gain coefficient to then block a lot of that solar gain. Now, if you want the view, that's okay, do it for the view. But if you want optimizing passive solar, you'd say, in this part of the building, I'm going to have a high solar heat gain coefficient. I'm going to put some, take some sun, use some maybe mass on the wall, a couple layers of gypsum. And then over here, where I don't have the flexibility of having mass, I'm going to put a low solar heat gain coefficient to block some of the solar gain, but I love the view. But that's the strategy here, is you want to pick where you want it and how you manage it, because too much solar gain is uncomfortable. Yeah. We designed buildings that were passive solar, and you're like, holy crap, it's hot in here, you know.
We actually had a code change a couple of years ago due to houses overheating, and no one's really realized why that's happening yet. But we tend to invite a lot of solar gain into our houses and aren't necessarily designing them to optimize that. It's just
And that's really poor shading, isn't it? And we're talking about overheating in summer.
Yeah.
But are you talking about overheating even in the cooler months, Mark?
No, I'm in swing seasons. So imagine this. So
Yeah.
if you look at optimizing shading, it's a critical function, right? Shading is everything in summer, but I'm talking about swing seasons, right? As soon as the sun angle gets up as steep as it does, you don't worry as much about that gain because you've got at least enough overhang to do full shading of the glass. It's the spring and the fall seasons where I don't really need heating, but I've got a solar gain because my incidence of solar on the building is low. So in the sky, the lowest level, of course, is in the winter. So that's where the sun angle is at its lowest. So then I don't mind the solar gain, and I've got a near incident level of solar gain on glass. I'm getting lots of gain. As that starts to pick up, and I get my swing seasons, that's the overheating cycle most often. So that's what we worry more about. Yeah.
Yeah, March.
Good question, Dave. Very good.
Yeah.
We've had a few discussions about this, haven't we, Darren?
I'm sorry about that. I'll keep remembering north.
Yeah, it's okay. We're all upside down here. I might just move on. We've gone, so our water layer, our air layer is the next one. We started to talk about that and why air seal the WRB.
Well, yep, but an air control layer is really more than the WRB, as you said. So what we want to do is to control the flow of air from outside in and from inside out. And there's a couple of reasons for that, right? You guys use fibrous insulation. Is that right, Greg?
Mm-hmm.
Yep. So fibrous insulation only provides its rated value when it's motionless, dry, and really fills a cavity completely. As soon as airflow moves through it or there's moisture in it, its R value and insulating value, I should say, drops in some cases dramatically. Compressions in the insulation, all those things interrupt the importance of having a layer of insulation. You only get one shot at this. You insulate the building once. Do it extremely well. Use a really good product. Make sure it's airtight on the outside so I don't have dust and dirt and air blowing through it. Make sure it's airtight on the inside so I don't allow moisture and other things to migrate through. Now, once I have a thermal layer that's airtight and sealed, its maximum R value can be achieved, its insulating value. And so if I take those away by letting the building be leaky, I not only lose control, which we've been talking about control, such an important thing, you guys. Controlling the interior environment. If I want to control air quality, temperature, I can't do that with a leaky building. You can't control leaky buildings. You can't engineer leaks. I'm going to just do a sloppy job over here, kind of over there, and hope I get enough air coming in around the building. It doesn't work, and we know that for sure. So tightly built buildings, properly installed thermal insulation, a well-done air barrier makes the building last 100 years or better. It now allows me to control heating, cooling, and ventilation.
Yep. Okay. So with our houses, basically the way we build, our primary air control layer is the plasterboard, or what you would call the drywall on the inside. And I've had this discussion about air sealing both sides at the WRB or our house wrap and the plasterboard for that reason. Because we're so focused on thermal, the understanding has to be made that that thermal value will not work unless we're dealing with the air barrier or the air control layer. So now the trick is to, and I probably shouldn't go too deep into this, but how to seal the drywall to the studs.
How tight?
Or how tight?
A tight house.
Yeah, well, okay. So first of all, how would you seal the drywall to the studs, Mark?
I'll do that first, just to make sure I get everybody freaked out. There's no such thing as a house that's too tight. I just want to throw that out there. So the way we normally do this is to take the gypsum, the plasterboard drywall, and you're going to secure that to the framing. As you all know, it's really difficult to get framing that's lockstep in straightness, right? So as the drywall meets that framing materials, we're using oftentimes a couple options. One are using gaskets. Gaskets have been around for a very long time. In the 1980s, the Europeans had what was called a APDM-P gasket. And it was just a little bulb gasket. They were using that to secure the drywall in Europe as well. Still being used as one of the primary air barriers. So you would tack the gasket to the top plate, to the bottom plate, and to intersecting locations, window framings. You would put the gasket on all those surfaces, then attach the drywall over the material so that the gasket then would be sandwiched. So if the wood shrank, the building moved a little bit, the gasket would maintain the seal. Still to this day would be considered a good strategy to seal buildings using a gasket. There are now products on the market that are actually spray gaskets, or gaskets in a can. So the gasket in a can allows you to have a spray gasket that you can spray on the framing. It never sets up, it stays soft, and then you can put the drywall straight onto that. So it's a less expensive approach. The contractors can slide around and kind of wreck it, so they have to be a little careful, where the bulb gaskets are a little easier to install more consistently. So the other pieces end up being sealants. So I'm a fan of sealants. I don't call them caulks, I call them sealants. I don't know what do you call them, but we use sealants. Sealants at the bottom plate, where the plate sits on top of the subfloor or on the slab. So the interface between the bottom plate and the concrete slab is a joint that's important. Sometimes people put that plate on a gasket, but that joint needs to be sealed. Yep. Then of course, the biggest problem we have for air sealing ends up being the lid. But at least on the walls, very straightforward. And the top plates become the other challenge to seal the roof. The lid is a really leaky spot.
Yeah, that was going to be my next question, because gasketing the wall's fine, and even the face of the top plate, but the sealing of the ceiling plane,
that's tough.
Yeah, that is tough. Yeah. And down lights, or what you call can lights.
Are they popular?
Yep. Oh yeah, yeah, they are. And no matter what we do at design stage, we'll go to a house and then it'll be riddled with those lights through the ceiling.
No doubt. So those are easy to deal with. You know, the industry in about 1991 started building airtight recessed lights. So all the lights install a gasket built right into the light. They basically in this marketplace, they don't cost any more. They're about the same price. So you buy an airtight recessed light. The light is now installed in a sealed can. There's a gasket around the front piece. You drop that in when the drywall goes on, it seals against the gasket, and you've done a normal recessed light leaks about 10 cubic feet per recessed light per minute. A sealed can leaks about 2 CFM per minute, so cubic feet per minute per light. So that's a pretty large reduction to go from 10 to 2 by just getting the light to have a gasket.
Yep, yep.
All the major light companies make an airtight gasketed light.
Yep, yep. So what's the major concern with air leaking through the ceiling into the attic space, Mark?
It depends on climate a little bit. So let's say you don't have much of too cold of climates to realize, but let's say that the climate was a little cooler. If warm, moist air from the house should ever leak out, you don't have too much moisture conditions either. If it leaks up through the recessed lights, it can find its way up into a location that's cooler, thereby condensing in the attic. That's usually one of the concerns why we would prevent that. The real game here is to make sure that if you look at the surface area of the ceiling, maybe you guys have maybe 1,500 square feet of surface area on that ceiling space. You can convert that if you'd like into square meters. But the idea is that if I've got the ceiling plane and I look at that being leaky to the outdoors, as I heat the building and air wants to leak out through the roof, the rule of physics is that if it leaks out into the roof space, attic space, it needs to then come in. It can't leave unless it can re-enter. So now I've actually made the problem worse. So an airtight ceiling plane is critical to stop the flow of air and to stop the flow of heat. The thermal insulation, if it's in there, but air is leaking through it, its R value, as we remember, drops significantly. Yeah. So you want to make sure that their insulation contact unit, yes, Richard, that's beautiful. It's called an IC rated can, but all IC rated cans aren't airtight. IC stands for insulation contact. That means it's thermally protected. So a light bulb that would get above maybe 200 degrees will shut off the light bulb. An IC rated can that's airtight is a different can. Just wanted Richard had that comment. IC is only thermally protected, not airtight. So again, the lid of the ceiling is now got to be sealed tightly, a bit more difficult to do. Oftentimes I've gone up into the attic after the gypsum is installed, the drywall's installed, and sealed it from the top side, because I can see all the light shining through, and it allows you to go back and seal from up there. That oftentimes is a little bit easier approach. You just have to walk along the rafters.
Yep, yep. Which can be tricky to do with a flat roof assembly.
It's really, you just got to get a really little guy to get up there.
The apprentice.
Um,
Just on that, is it better? Is that a better approach than to use internal membranes?
Well, yeah, I would say that internal membranes are nice. I know that people struggle with that. Now they make vapor permeable membranes, and Majav is one of those internal membranes. But I've seen many people install an interior membrane across the ceiling, make it part of the airtight enclosure, then install the gypsum, and that works beautifully. So I would say that an airtight membrane on the inside, as long as it's not vapor tight, is usually a good strategy. In the US, we have vapor control layers that have the ability to change their permeability based on vapor pressure. But usually the membranes, as long as they're not complete vapor barriers, usually function quite well.
Yep, yep. Very good. One other thing to talk about briefly with the ventilation of that roof space. We've had a code change here that says we need to ventilate our roofs or our attic spaces. What I'm seeing a fair bit is people put a turbine sort of whirlybird on the roof, but nothing at low level. And I've actually had a circumstance where I went to look at a building where there was water dripping through the light fittings. They tried to fix it by ventilating the roof, but they made it worse by drawing more moist air from the house up into the lights. So what are your thoughts on roof ventilation like that, Mark?
Well, I guess that the idea on ventilation was really just designed in building enclosure research that was done where we ventilated roofs both at the eave and at the ridge, and saw that as air came in, it was able to provide, in some cases, in some climates, the ability to keep the roof deck cool, that surface cool. And there really isn't a lot of that happens. Temperature differential isn't dramatic. Airflow from outside, whether it's winter or summer, the air coming in is really not doing a lot to change temperature differential. You guys get a little bit more of that because you've got a space above there which is not sheathed, but there's not a lot of temperature removal. There's some, but not dramatic. The moisture removal rate is a little bit better, so that it needs to happen at the bottom of the ridge or the edges, up through the outside, along the roof edge, and then out through the top. That's preferred. If you don't do that, in California, for example, we have a little bit of problem with fire. I know you guys had a bout with fire that was worldwide brutal. I felt for every one of you that had to experience what you went through. I think it was last summer, huh? And it was a very horrible thing to watch. And what was happening is some of the embers from outside during the fires would get sucked in through the vents and then get into the attic space and create a problem there as well. In some parts of California, we're starting to reduce the amount of attic ventilation, realizing that as long as you have an airtight lid in the ceiling, you're not trying to ventilate the attic now. So if the idea on the attic was to ventilate house moisture from getting into the attic, let's not do that and prevent that from getting into the building as well. So again, an airtight lid, an airtight wall allows me to control the interior of the building the way I'd like to. Once the moisture or the building assembly the moisture inside the building leaks outside of the building assembly, I've lost control. I don't know where it went. I don't know what it's going to find as it leaves, but that's the improper approach. Ideally, I would have a ventilation system that said, I'm going to take the air in the house, exhaust it outside, bring the same amount of fresh air in, deliver it to the occupants, and I'm going to control the interior environment by filtering and managing the indoor environment. Now I've got a much better way of taking care of that. So I would say attic ventilation, we see it done where they reduce it, where they put too much in, but the strategy here is that small amounts of air in the attic can do a nice job of maintaining a control of any excess moisture. As long as the lid's tight, I'm not putting too much up there anyway.
Yep. So you wouldn't recommend exhausting your toilet exhaust fans into the roof space, into the attic?
Never. No, that's good vented to the outside. I saw one comment here, filling the cavity with insulation prevents conductive looping is not necessarily the case. Density is what improves that, just because I keep going through that. Most insulation is at 1 to 3 pounds of density. You have to get your densities above 4 pounds in order to reduce convective looping in the insulation. So, yep. It said whirlybirds are not a practical solution to venting the roof cavity. That's true. And we are finding mechanical ventilation has to be ducted to meet the building code of compliance. So getting the getting whatever you're trying to vent out of the building should be removed from the space and out of the structure. Do not vent it into the roof.
Yep, yep. Now we're technically still allowed to do that here, but it's not good advice. So
they still do it in Oklahoma, and they have lots of problems in Oklahoma. So it's not an Australia thing. It's people not caring about the physics. So it's a math and physics problem. You don't dump moisture into an unconditioned space. Don't do it. So I don't need a code to tell me that. I just know it's bad physics. So don't do it.
Yep, yep. Okay.
We're not really talking about ventilating the roof for that purpose, are we? We're talking about ventilating it regardless of where the other moisture is going.
Yeah, if I could keep the moisture out of the attic space by venting those bath fans or any other conditioned spaces outside of the structure, and I have a nice airtight lid, the amount of moisture moving from inside the conditioned space of the house into the attic is quite small. So then if I do have a small amount of attic ventilation, I mean a small amount, it'll allow vapor diffusion in the molecule state and molecular state to then move up and travel outside the building assembly easily. Large amounts of water, you're done. So that's why we flash well. If the building leaks rain, it's over, right? It's over. If I'm looking at vapor moving back and forth, wood frame buildings are amazing. They can take on some moisture, give it back up, take it on, give it back up for 100 years. If you overload a building with too much, it thinks it's sitting on the forest floor, it begins to rot. So all we have to do is appreciate that this wood building can take something. Greg, you brought this up earlier. You have a forgiving climate. Don't push your buildings past their level of forgiveness. Build an airtight building, insulate it well, ventilate it properly. Now, what it does see seasonally, it can handle. Just don't load it up with whatever the occupants are doing.
Yep. So that brings me back to one of the unintended consequences of what we've found since, and you started with this over 20, 30 years ago in the US. Since we started insulating buildings, we've decreased the energy flow through the building, which is great for energy efficiency, very bad for drying. So what we've done is what you've just said is overloaded the capacity for that to dry. What our traditional buildings were, they were built out of more resilient materials, hardwoods and whatnot. They leaked like a sieve and they weren't insulated. So any water moisture that got in would just dry out.
Correct.
Now we insulate, we've slowed down that energy flow, and therefore we're creating potential for moisture problems.
It's just the retainage of water is, if you look at European buildings, most of them are masonry. A European masonry building takes on a tremendous amount of water. There are no organics in it to rot, and it will dry over a period of time. If we're going to use wood, we have to appreciate the fact that it's a tremendous resource. It's a efficient cost thing to do. So if you choose wood, appreciate its resource. As a wood product, it's amazing. It's grown, it stores carbon. What a great product. Just don't push it past its capabilities. If you're going to build a building out of masonry, realizing that it can take on both a hysteresis of heat flow, right? It can get warm during the day and cool off at night. We all know that that's possible. But pick the strategy in terms of the structure you choose, then don't push it beyond its capacity. Yep. Wood frame buildings can be beautiful and they can rot profusely if you don't manage water. It's really obvious, yeah.
So talk us through, another thing that's starting to happen here, but not to a great extent, is a rain screen on the external walls. Traditionally, most of our houses are probably brick veneer. So by default, they have a rain screen.
They do.
With our clad buildings, weatherboard and sheet, generally we have our house wrap and then the sheeting just gets smacked straight onto that. So better advice is to have a gap in a rain screen. Do you want to just talk through that and the importance of that?
Yeah, and that's a challenging thing again. So when you don't have sheathing, but you have a weather barrier there, you do have a little bit of flexibility in the paper into cavities. So that it isn't laying flat and tight. When we sheathe our buildings with OSB or plywood, it's a very, very flat, very tight surface. If I put siding up against it like that, the backside of the siding gets wet. Even if the weather barrier is on in place, the backside gets wet. If it's a wood-based siding or a cement-based siding, which is very popular in your market, the potential is for the cement-based siding to then pick up the moisture and maybe push off the paint films. The benefit to a rain screen is that it separates that enough, about 3/8 or about 5 to 7 millimeters, away from the building assembly, allowing drainage to occur. And when you get up to the 8 to 10 millimeters spacing, it allows drying to occur. So the back of the siding stays at a similar temperature to the front side. The drying and the moisture level stays in the same plane. You can have paint films that last 20 and 30 years. So the idea is a rain screen is to protect the cladding system. You don't need a rain screen behind metal claddings usually, but you always need a weather barrier. As soon as you're going to look at that cladding, the type, if is it absorptive, can it absorb water, and will it challenge its success? Or if you space it off the building. All buildings that have a space behind the cladding usually lasts longer. Remember, if it's metal, I can't fail the metal cladding. If it's wood or cement, I have a greater risk of challenging paint films and the durability of the cladding.
Yep. Okay.
Screens for cladding.
Yep. Okay. So with a metal cladding up against the wall wrap, basically when vapor drive's coming out through the building, and that wall wrap is vapor permeable, it's going to condense pretty well on the backside of the metal cladding or the outside of the WRB.
If the surface temperature is cold enough to do so.
Yep.
So what you'd have to say is that it would have to have the temperature of the metal would have to be below the dew point of the moisture coming through the building assembly. So if you're getting maybe below 50 degrees Fahrenheit, you would say that the potential for condensation there then increases. If you do have a concern about that, I'm trying to tell you that if you have an airtight assembly in the inside surface, I don't have very much moisture moving through the wall, right? So an airtight inside, an airtight exterior means that I'm keeping the insulation motionless and dry. Now that wall doesn't have a transfer of airflow, all I'm dealing with is the molecules of water that want to move through the assembly, which is remarkably slow. It's called vapor diffusion. The diffusion rate is very slow. So if it moves through, there's a little gapping in the metal cladding. It could then vent up and out if it's a small amount. If it's a large quantity moving through, then it could condense on the metal sheathing and give you trouble. If you are a colder enough climate where you're going to see a sustained cold temperature, furring the metal cladding off the building with a rain screen would then allow airflow to occur and dry that more effectively.
Yep. Okay. So it just highlights the importance of the airtightness of that wall assembly. And to throw statistics or percentages out, 97% of moisture in an assembly comes through air leakage, not vapor diffusion.
That's correct.
Yep.
It's such a substantial issue that you can't control liquid water. That's the big bucket dumping in the wall. That just sounds incredibly stupid. How are you going to manage that? I can't dry that. I can't do anything but stop it from happening. Yep. Because once the liquid water gets in the wall, vapor diffusion is not going to dry the assembly. That ain't going to happen. It's going to take years. So the idea is build watertight assemblies, build the building so rain can't get in. Build it airtight so airflow doesn't travel back and forth across the wall. Yep. And now the moisture molecules that can move back and forth could either get maybe picked up by the wood, could dry to the interior, and then be moved through the building assembly. You've got to make sure you maintain the big ones and then let vapor diffusion sort itself out.
Yep. Okay. Now, we're going to run over time if I keep on like this, but I just want to mention one more thing about the wall assembly. As far as solar heat on the wall, if we're talking about a metal cladding that's right up against the stud, the solar air temperature or the heat temperature in the summer of that sun hitting that wall, when we're talking about heat transfer, our UA delta T or temperature difference between inside and outside, our solar air temperature of that wall on the outside is horrendously high, much higher than the ambient air temperature. Yeah. So a rain screen, batten, or some thermal break on that. What are your thoughts on that, Mark?
That, of course, could help. If I had ventilating at the bottom and it ventilated at the top, it's the same thing as trying to keep a roof deck surface cool. Yep. But remember, if that surface is running 160 degrees Fahrenheit in the summertime when it's being heated, it would take a lot of airflow on the backside of that material to cool it down very much. Thereby, you'd say an exterior level of insulation. If I put exterior insulation on the outside of the building, that would then inhibit it from moving back through to the inside. Yep. So as you probably would like to discuss, this could take days. But the idea there is that if the insulated cavity, and you're really trying to isolate it from outside, you would put a rigid layer of insulation on the outside of the framing. That would interrupt the framing studs, and whatever cladding was installed over it would not transfer its energy back in. It would then be reflected back out. If the wall gets very hot, the R value of an insulating piece of wood is about 1 per inch. Fibrous insulation is about 3.5 to 4 per inch. So you can imagine that a lot of studs can have 25 to 30% of the wall has a lower R value because of the frequency of framing. So exterior insulation would then interrupt that issue of a hot cladding transferring its energy in.
Yep. One of the details we see quite often with external insulation, and I don't think it's really intended for external insulation, but what they do is they put about a 1-inch batten on the outside of the stud, and then the external insulation on that. So we have a 1-inch gap between the external insulation and the stud bay. So do you want to just give me your thoughts on that system?
Yes. Well, I would hope that that's pretty clear, that you wouldn't put an airspace that allowed outdoor air to move through it. It's like putting a coat on that really, you had a space between your coat and the outdoor air moving up underneath your coat. It wouldn't be like wearing a coat. So it's important that if the thermal insulation is going to be part of the building assembly, it needs to lay in contact with that. As soon as I cycle the air past the insulation, its insulating value drops dramatically because it's really not doing a good job of insulating the cavity. I've really kept that space more at the outdoor temperature. The idea was to put the insulation on to then kind of fool the wall into thinking that the heat flow and the energy flow has been interrupted here from the direction of warm to cold. So it really depends on which way it flows. Having a gap between the insulation and the building lowers its insulating value. Now, that said, if you put insulation on the outside and you made the space around it airtight, it then could provide insulating value. But that would kind of defeat the whole purpose on what you were trying to accomplish. So if you blocked everything off and had no airflow in that cavity, the thermal insulation could perform its function fairly well. Not as well as up on tight, but it could perform a function fine. As soon as there's airflow between the insulation and the wall cavity, you lose.
I wonder if we could just touch on whole house ventilation, Greg. There's a really good question there about ERVs and alternatives to that.
Yes, and I did want to get into that, and we haven't got a lot more time left. So, but yeah, Mark, the ventilation in our houses is something that we don't really think of much. In our building code, it's basically open a window. But when we're doing a higher performance house with our water, air, vapor, thermal layers, all controlled well to a good air tightness strategy, can you talk us through the strategy of how we do a whole house ventilation system, or what is important?
Yeah, it's a great question, Greg. If you look at, here's the strategy we often hear. Somebody will say, so you're going to tell me to build an airtight house and then you want me to put a ventilation system in? What's wrong with you? Why don't I open the window or punch some holes in the wall? And you're like, okay. Remember, what we're trying to do is to control. So if I open windows, an open window is a good strategy. It provides ventilation. It doesn't provide me any control. I don't know, when am I going to open the window? On windy days, on dusty days? What about rainy days and foggy and cloudy days, or if there's a temperature inversion? What about those days? Well, no, I'm not going to open the windows on those days. So that would be called intermittent ventilation. So I don't know if you're able to interrupt your breathing rate to affect the outdoor conditions, but that's what sounds so stupid, right? The outdoor conditions are bad. The pollens are high. Today I'm going to hold my breath because otherwise I'm going to have some allergies. The idea is that you build a building so that it can mimic and introduce ventilation at the rate I breathe. If you want to open the windows on a beautiful today, right now in my house, I have the windows open. It's beautiful. It's 60 degrees outside. It's gorgeous state of ventilating. But tonight it's going to get down to 45 degrees. I'm going to close the window. Now my house has a continuous level of ventilation and it runs all the time and uses a small amount of energy. I know that whether I have my windows open or closed, my building is continuously ventilated. In the summer, it's 100 degrees Fahrenheit here. I've got my ventilation system bringing in just as much as fresh air as I need for respiration. I breathe about 9,000 liters of air a day. I want to make sure that because it's uncontrolled, I have no way of interrupting my breathing cycle. So I would like my ventilation to represent my respiration cycle. So the strategy here is build a tight building, provide continuous ventilation. The ways to do that are basically three. Exhaust-only ventilation. If I put a fan in the house, a very good quality Panasonic or Braun fan uses 20 watts of electricity. It's insignificant. They cost $150 US. So if I put that in the ceiling, I turned it on and ventilated it out. As I'm running that fan somewhere, somehow in the building, it can't leave if it can't come in. It has to come from outside or potentially from under the slab. So let's say I got a fan and I'm going to bring air in and blow it out the ceiling. I'm going to blow out the energy, but I'm going to replace it with outdoor air. I don't know where it's coming from. Could be where the dog kennel sits or could be near the garage, but I don't have any control. Another approach, which we see here in the South, is to use what's called supply side ventilation. I'm going to take a fan, I'm going to turn it the other way. I'm going to go and find a good location with fresh air, and I'm going to blow fresh air in the house. And blowing it in the house, it's going to start to blow the house up, right? So now the air's got to get out. It's going to leave through cracks and seams, but at least I'm introducing fresh air. I could then control that by filtering it as well. So let's say I've got a quiet fan, a filter, and I blow it to the inside of the house. Would that be considered ventilation? I'd say, yeah, as long as I controlled the outdoor air, brought it in, filtered it, and delivered it on a constant basis, that would be a controlled way of ventilating a building, a low cost way of ventilating a building. Now, the last one would be balanced or energy recovery ventilation. Now, I got involved in energy recovery ventilation in about 1986. And the ideas were that we can take and ventilate a building, exhausting air out and introducing air in at the exact same rate using one motor operating two pulls from outside, one blew air out, one brought air in. In doing that, I could recover both the energy, so the heated energy goes into the cooled energy in whichever direction, whether it's outdoor, it's cool, and coming in, the heat from the house is able to warm the fresh air coming in. In the summer, it's reduced. The hot outdoor air is cooled by the air that's exhausting from the air-conditioned space. So that's an energy recovery component. The ERV part is moisture, and that's an enthalpy control. What it allows me to do is, in the wintertime, I'm not sure, but do you guys get cold? I mean, do you guys get dry inside the houses? Your house is dry inside.
We don't really get dry so much.
Okay.
There's a whole discussion to have about ERV, HRVs here, I think, which I haven't gone into depth, but yeah.
Yeah, I would say that because the ERV recovers about 40% of the moisture that would normally be exhausted outside, a normal house with some baseline ventilation, we find that in almost every climate zone, from Minnesota in the north to Arizona in the south, an ERV works in all of those climates well to kind of manage and balance humidity. I would like to have 40%, 45% relative humidity in my space. That's good for my lungs, good for my wood furniture in the building, good for the wood flooring, the cabinets. They would like to be in that moisture range. If you ventilate a house with an HRV, all you're doing is you're going to eventually dilute the moisture levels down that you're producing to a level that now it is probably too dry. And we found that out oftentimes in cold climates. People were ventilating in cold climates. The houses got so dry, they shut off the ventilation systems. So now what we do is use ERVs to recover some of that moisture. And in the summertime, it rejects some of the humidity that would come in and challenge my air conditioner's ability to dehumidify.
Okay. Okay. That's good. So really what we have here with our situation is we don't have a lot of ERV or even HRV systems on the market, and the ones that are quite expensive.
Yeah.
So our starting point that I've been dealing with is basically an exhaust only fan, like a Panasonic fan, that works.
Sure does.
And until we get, and also that works around 3 air changes per hour. When we're doing a house here, that's achievable with our construction methods without going too far from standard, without going down the passive house route of, changing the assembly. So around 3, we can get there, and with an exhaust-only fan, we're still okay. Once we get below 3, though, we're really heading into something where we need a balanced air system. And I suppose one of the challenges and the tricks we have here is to advise people on what to do within the current construction methodology without overloading the price, but by providing a good result.
Yep, and I think that you'll watch. It always takes this, as we know, supply and demand is the way the world of economics works. As you look at ERVs and HRVs here in this country, we see some of them run between $500 and $1,000 for the unit. You guys probably pay a lot more for that just because someone's taking advantage of you. But I would say that there's a lot of opportunities, even if it's $1,000, fairly small amount of cost to provide healthy air for my buildings. Am I willing to invest in my air quality for my family? And does that matter to me? I think it's probably one of the most critical things. I've been involved in ventilation my entire life, Greg. You said just recently is one of the places I cut my teeth on. I spend most of my time nowadays looking at the idea that ventilation, since COVID, it was a part of the strategy. 2 weeks ago, I was in a restaurant in the California coast, and they've decided that increasing the ventilation rate and providing filtration allowed the building to get so that it managed its energy flow, but had the same air quality as being outside on the patio and living outdoors. So ventilation is critical. How you achieve it also matters. You said that exhaust-only ventilation can work in most cases. I would agree that that's true, except always remember something. When you go to exhaust-only ventilation, you do not know where the air is coming back in. So we call that the origination of air. When I depressurize the building, I'd say, where did it come from? And you're like, around. I'm like, I don't know. Could it come in from a garage? Could it come in through a flue? Could it come in through an area near where the garbage cans are stored? I have no control. So unless you intentionally know where the air is coming in. So the Europeans created some diffusers, and there's a little pop vent. And what you would do is you would pull the little cord, you would pop the little vent out and provide a controlled leak. You'd have an exhaust fan someplace else, a controlled leak, which would bring fresh air in and say, I know it's coming in from there, not from some unknown source. Otherwise, we turn the fan around and push the fresh air into the house. And in many climates, that works effectively to now let at least I know the fresh air is coming in and it's going to leak out of the building. As long as it's fairly well managed, that works. But I don't think there's really a magic number. I think I would want balanced ventilation at 3, at 2, at 1, at 0.6. I like balanced ventilation because I know where it comes in. I want to filter it so that I reduce pollens and dirt. I want to know it's going back outside, and I want to know where it goes. So if I really want control, and I think that's what people want. If you're driving in your car, you wouldn't believe how airtight your car is. I've got filtration in my car. I've got controls. I can dial it up 71, 72, 70, pick the temperature. The way you control an interior environment that you're going to live in for your life is to make it airtight, properly ventilated and conditioned. And then you'll have a much safer, healthier, and more enjoyable space to be in.
Yep. So, and a lot of this is educating people, the designers, the building surveyors, the builders on how to do this. A lot of the time, we see designs with cavity sliding doors or pocket doors, as you call them, between the garage and the house. If you're making everything else airtight, then you're just asking for trouble there. Yep. So there's this level of understanding. We need to really know not just how to do it, but why we're doing it, and then implement everything as a system to make it work properly.
I was just asking about blower door tests, and that's just a way of quantifying the airtightness, isn't it?
Exactly, Darren. That's a great question. Blower doors have been around. I saw my first blower door in 1983, and we were using those in retrofit buildings. And so we would install the blower door in the front. It was pretty crude, but we would depressurize the house, and then we would see what CFM at 50 pascals, how many cubic feet per minute we would be able to pull through. And of course, the numbers were fairly high. People would go around in the attic and around the house and start caulking things. And when we reached 1500 CFM exhaust, everybody would yell, stop. We'd shut the blower door off and turn off the caulking assembly and see that we kind of got it pretty tight. That was the strategy in 1983. The idea was that a blower door is going to help me normalize the fact that I need to know how big the hole is. And that's basically all a blower door does. It says, is the hole this big or is it this big? I need to know, because I can't size a heating system, a cooling system, or as Greg alluded to, a ventilation system, and unless I know how big the hole is. If I then have the size of the hole, if leakage and infiltration represents about 30 to 40% of the energy loss in the building, why would I not want to know that? How do I size a heating and cooling system if I have no idea where 30% of the energy flow is going? I'm going to guess high. If I want to right size equipment, I'm going to use the blower door to depressurize the house, find out how much air is leaking in, give that information to my heating contractor. So he goes, based on the insulating value of the wall and the air tightness of the building and the performance of your windows, you need a 2-ton air conditioner. I was going to put in a 5. You don't need it because I did the math. The math is air leakage, thermal integrity in the building, and solar performance on the windows. That's how you size heating and cooling. So if you really want to control your indoor environment, you have to do those things, and then a blower door test validates that. Our code will require every house in the US will have to have a blower door. That will be the code of current status.
Yep, okay. So speaking of heat loads, we've run over time, so I shouldn't keep this going for too long. In establishing a heat load, that's one thing. We've had this discussion over the phone, Mark, about contractors in the US as well. They basically just base it on the floor plan. This is how big the house is, this is how big the heater needs to be, or the air conditioner, or even the ventilation system. Do you have any good recommendations on how to do a good basic heat load?
Yeah, I think that there's a couple of different ways. Of course, there's wonderful software. Manual J has been in version 10, so it's been around for a very long time, 25 years. This isn't new stuff, folks. Yep. All we got to do is punch in the insulating value of the wall, punch in the air tightness of the building, and the window performance on the sticker. You put that into the software calculation, and you pick your location. Where are you? You put that location in the software, and it says, based on where you're located, here's how much energy is going to move back and forth across the building over a year. You'll need this much for heating, BTUs per hour. You're going to need this much for cooling in BTUs per hour. So this is the right size system. Then you would match the air conditioner with the furnace so you would have an optimum way of controlling that. The old rule of thumb was about 400 square feet per ton of air conditioning, which is absolutely absurd, 1985 specifications. Today we have houses, I'm building my own house, and I'm at about 1,200 square feet per ton of air conditioning. I have a little air conditioner, a beautifully controlled building, and I've got just enough cooling to keep me at 72 degrees when it's 110 degrees outside. And I'll use a small amount of energy because I built the building enclosure to be tight. Windows are high performance. They're actually triple glazed in Arizona. And the building will now have minimal needs for energy, continuous supply of fresh air. My energy bills will basically be zero. I like that. I like that my energy bill in Arizona, people here in Arizona have $500 to $700 a month electric bills when you're trying to cool. Mine will be nearly zero. How much money do I invest in my house to monthly save $400 to $500 a month? If you look at that amortized over a loan, my return on investment will be 18 to 20% minimum. And where do you get that? Not at a bank, and sure not in the stock market. So investing in a building means that over the life of the building, however long you own it, if you're saving energy, the building is paying you back for whatever you invested in making it better. It will then sell more in the future. Imagine if I'm in Australia and I have a house with a very low energy bill, would that add to the value of the house? If someone was coming in and Darren, you're coming in to buy my house, I go, by the way, it's going to cost you about $50 a month to heat and cool this building. Would that have any impact on what you would be willing to pay for that house?
There's actually a scheme in the Australian Capital Territory, Canberra, where they do energy assessments on houses at point of sale. So they've proven that a better energy rated house sells for more money.
And faster. Yeah.
Yes.
Yeah. And I think that's really logical. We're not talking about things outside of basic stuff here. This is so critical. And I know, Greg, you worked hard on this. We're talking about physics and math and proven principles for the last 50 to 100 years. We know how to build good buildings. In Australia, folks, what you need to do is execute on it. There's no more discussion about whether there's good math. It's really simple math. Heat flow and heat loss is UA delta T. It's been around for an incredibly long time, since ASHRAE really began doing heat loss calculations. I know where the load is. I know how heat flows from warm to cold, how air leaves buildings. We all know that. So trust the math, trust the physics, and begin building buildings that perform like that. There's no waiting for the shoe to drop. This is what you do starting tomorrow. Take advantage of all the world's research and all the failures. You guys get a chance to go, cool, everybody else got to see the failures. Now we're gonna build these great buildings in Australia, and everybody's gonna go, wow, you guys are amazing, which you already are. Yeah, I think you're one of the great groups on the planet, actually, one of the most beautiful countries in the world. And you guys should be doing that, leading the world in terms of high performance buildings too, because you're so good at everything. You make great beer too. So I would strongly encourage you to do a great job building great buildings.
You haven't tasted my home brew, Mark. You could take that comment back. It's horrible.
I think that we can always improve something. So I would say that all you have to do is go forward, right? We can fix the buildings. There's 130 million existing houses in the US. Most of them are in pretty poor shape and need to be improved. I worked with a group called Hayward Score. They're rating the quality of and health of buildings, and they're showing that they're not very good. So what we got to really do is build the new stuff. Make the new stuff well done. Yep. Don't build any more houses that are leaky, drafty, and poorly insulated. Manage the rain and the control layers that Greg mentioned. Do that now and put those houses there. And then we can go back and try to fix some of the other ones that are challenged. But don't build any more inferior houses, guys. You don't need to do that. The cost is low. The benefit's high. It's just the right thing to do if we're going to move this culture and this strategy forward.
And we do have a slight advantage here with our building code. It is performance-based. So a lot of what I do are performance solutions. So we can put all this together in a package and just roll it out now. We don't have to wait for codes to change.
Yes.
If we know what we're doing and we can put it together properly, we can produce that sort of stuff and give people really high quality outcomes right now. There are a lot of builders listening in now who have really tried this. They're getting good at doing air tightness. They're getting quite excited about this. So it's not that hard to do. If you understand what to do and why to do it, it's not that hard to implement it. So,
yeah, I'm going to leave you with kind of two quotes. One of them is the one from the former CEO of Ford Motor Company. He said, if you don't like change, you're going to like being irrelevant a lot less. I think that's an important one to consider because that's just the truth. But the one I really want to close with is that if you look at it, there's a carpenter's guide called Audell's Carpenter Guides. They were published, they really first started making them in about 1920. First one I'd seen was in 1930s. And there were a series of 4 books. They were about that big. They would fit in your back pocket. And they were beautifully written on how to build in carpentry, how to do joints and seams, pick drill bits. So it was just amazing stuff. And in the inside cover of that carpenter's book, I want to share with you a quote that you all should hear, because it's a carpenter's book talking to what it is our responsibility. And it's written by a fellow named, I'll just think it's John Ruskin. So John Ruskin was born in 1819, died in 1930. I wanted you to listen to this quote. When we build, let us think that we build forever. Let it not be for present delight or present use alone, but let it be such work our descendants will thank us for. Take the knowledge of the day, which we just shared today, and put that into our buildings, because it's what we owe the cultures and the kids and the future generations, to take the knowledge that we do know and put that into future buildings. So I sure encourage you all to continually research and learn. Listen, thank you for coming today. What a great step. But there's a lot of people that know a lot of information, and I appreciate, Greg, you giving me that opportunity to come here. Thank you for this.
Oh, look, Mark, thank you so much for doing this for me. You've been a great mentor of mine since I first met you, and I really appreciate the phone calls and the advice, and especially to come along today just to talk to everyone, share your knowledge, and reinforce to people that I'm not nutty Greg with my crazy ideas. There is some basis to what I'm talking about.
Yes, well, again, Greg, you deserve a lot of credit for the fact that you sourced out the education to learn, and now you're trying to share it with the people of your great country. You guys live in a beautiful place. I think it's a great thing to just begin executing on what we know so well. So good luck. And Darren, it's a pleasure to meet you as well.
Thank you, and likewise. And Greg's spoken very highly of you, and it's been very informative today. So I really appreciate it too. Thank you.
Well, I hope, Greg, we can do this again. And whenever you'd like to do that, I would enjoy doing it. It's of course something I would do for you at any time, Greg. So if you find a date or a time or a place, let's keep talking this dialogue. The more we share with each other, the more we mentor each other to do a good job, the better we get.
Yep. No, we'll definitely do that, Mark, because every aspect of what we've spoken about today, we could really barrel into and go in depth. But today was a great overview, and I really appreciate your time. So thank you very much, and I'm sure we'll do this again very soon.
And if anybody doesn't want to look up, remember Construction Instruction, it's a free app. It's been around for 13 years. About 200,000 people utilize it. It's free. It's got 10,000 assets on it, from videos, animations, graphics, all kinds of stuff. And again, it's free. So please.
I've got it on my phone too. Yeah.
Yeah, no, and definitely go to the CI website as well. And I would encourage anyone just to go over to, once we're allowed to leave the country again, go to Denver and
come to Denver. It's a beautiful place. And thanks, you guys.
Love to.
Thank you very much. Thanks, Mark. Thanks, Darren.
Thanks. Bye.
Bye, both of you. See you, Greg.
See ya.